Let me go into slide show. Right, actually I am Mr. Thomas Musora from Zimbabwe at Chinhoyi University of Technology, a lecturer in the Department of Mathematics. I'm here to present a paper on sales forecasting of perishable products, a case study of a perishable orange drink. I have got four authors. Yeah, that is Mr. Jaison Absalom, Mr. Jablani, Mapurisa, Dr. Chazuka, and Kamusha Joseph. So you realize for any organization which is involved in trading or manufacturing, the ultimate goal will be to maximize profits and minimize losses, especially if faced with this scenario whereby you are trading or manufacturing a perishable product. If you are in the manufacturing section, you would want to manufacture in the items which will all be sold, so that you won't experience returns or you won't experience dead stock. If you are in the retailing sector, you would want to order the number of items which will all be sold, so that you won't experience a loss due to dead stock or as a result of loss of potential revenue if you order less. So in this case, we are faced with a scenario of a manufacturing section where a small company is manufacturing a perishable orange drink. If an orange drink is perishable, it means it has got a finite shelf life. In this case, they are trying to optimize on the number of cases which they can manufacture. How do they do this? They have to forecast future demand. The forecast plays an important role in planning and optimizing. In order to do this, they approached us as consultants. We attempted to solve the problem using time series analysis, whereby we fitted an integrated autoregressive moving average model to the data and made attempts to forecast future demand. The data was from 2010 to 2022. As for this month, they have since reported minimum returns. Model diagnostics were done to the fitted models, and we realized none of the assumptions of the time series were violated. In addition to the usual diagnostics for time series models, we further went on to regress fitted values against observed values. And we realized the model which we fitted represented the situation well. Now, realizing the homogeneity of my audience, in order for us to optimally benefit from this presentation, I will take you through some concepts of time series, though I understand very well time series analysis is quite a wide field. I'll present maybe what a time series is. A time series is simply an indexed collection of entities over time. In this case, we are focusing on manufactured packs of orange drinks over the period from 2010 to 2022. So the time series helps to identify any recurring patterns which may be useful in forecasting future values. How do we proceed? We use the box checking technique, where we have model specification, model fitting, and model diagnostics. On model specification, we are trying to identify, is the model a moving average? Is it an autoregressive? Is it a hybrid? On model fitting, we are trying to estimate parameters of the proposed models. On model diagnostics, we are trying to check if the model is good or not. If it is good, we then proceed to use it in inference and forecasting. If it's not, we go back to model specification till we find the most appropriate model. Then a stochastic process. This one, I think I have already alluded to this. I'll focus on the mean function, which is, for those who are not mathematical, the expected value is simply the mean. Then the autocovariance function is the expected of ZT minus mu T. Then we have got ZT minus K minus mu T. Then the expression goes like that. Then an autocorrelation function is represented by that expression, where we have got rho K being equal to gamma K over rho naught. Then the partial autocorrelation function is the correlation function between ZT and ZT minus K after removing the effect of intervening variables like ZT minus 1 to ZT minus K plus 1. Then we talk of a stationary time series. A time series is said to be stationary if it has reached an equilibrium. That is, it no longer depends on initial conditions. Right. I talked of a moving average. Or a process is said to be a moving average process if it can be represented in that form. You note we are regressing over the error terms. The ATs are the error terms. Then Q is the order. Then for autoregressive process of order P, we are regressing over past observation. In this case, we are regressing over past cells. Then what did we do if a process is not stationary? You have to note, we cannot fit a model which we will use for forecasting to a non-stationary series. So we have to make it stationary before we proceed. There are various ways of making a series stationary. You can do log transformation, you can do square root transformation, you can do differencing, you can do moving averages. But in this case, I'll zero in on the differencing part. So that triangle represents, the inverted triangle represents the backward shift operator, and it translates to ZT minus ZT, ZT minus ZT minus 1. How do we determine the degree of differencing? You have to observe, after differencing, you observe the time series plot. If it reviews some stationality, that is maybe the Dick-Fuller statistic or the Dick-Fuller test is showing the series now stationary, or simply you observe if it's oscillating around a certain mean and there is constant difference, then the series is stationary. Right. How do we fit a model? For you to be able to fit a model, you have to exhibit the technique of the ability to study the ACF and the PACF of the fitted model. What is ACF? That is the autocorrelation function, that one which I showed you how it is determined. Then PACF is the partial autocorrelation function. If an autoregressive part is evident, you expect the ACF to decay exponentially, and the PACF will cut off at leg P. If the process is a moving average, you expect the ACF to cut off at leg Q and the PACF to decay exponentially and may contain damped oscillations. If it's a hybrid, you expect both the APF and the ACF to decay exponentially and may contain damped oscillations. Right. Armed with that, maybe we can now move together. For those who would want more, you can consult the committee and they will give you my contact details. We can move together. So for our data, the original data, we plotted the time series plot, and you realize there seems to be a trend. This data is not stationary. It has to be transformed to make it stationary. Like I told you, you can't fit a model to a non-stationary series. So we different. You realize the data is now stationary. There appears to be some constant variance. So from here, we can proceed to propose some models. How do we propose? I told you, you have to observe the ACF and PACF for the difference data. With that, that is the ACF. You realize it shows some significant spikes at leg 2, which seems to be repeating. So there is some seasonality. And there seems to be some negative damped oscillations. So we proposed an ARIMA model. The PACF has significant spikes at leg 2 with some evidence of some damped oscillations. So we proposed still an ARIMA model. After this, you try a number of ARIMA model. You would expect ARIMA 2, but when we fitted and performed diagnostics, that wasn't the best model. So the best model was based on this. The final model estimates, there was an MA1 and a seasonality element of order 12. Then you see the p-value significant. Then from after going over the model diagnostics or the model specification, we settled for ARIMA 011 for the non-seasonal part and 011 for the seasonal part. Right? Right. How do we proceed with the model diagnostic? If the model is good, the residuals have to have zero mean and constant variance. They have to be independent of each other. They have to be normally distributed. How do we see the zero mean and constant variance? You plot the residuals against fitted values, or the residuals against observed values, and you see the pattern. If they are independent of each other, a plot of residuals against fitted should have no pattern. If they are normally distributed, the histogram of residuals has to exhibit the normal distribution. Or the normal probability plot has to be a straight line. Let's proceed. Those are the outputs. You see the normal probability plot is almost stationary, is straight line, meaning the normality assumption is not valid. The histogram is almost supporting the same. Residuals versus fit is exhibiting no pattern. So no correlation of residuals. Then the other assumption of independent of each other of the zero mean and constant variance is evident from the fourth plot there. Right? We did further diagnostics using the ACF and PACF of residuals for the proposed model. If the model is good, the ACF plots and the PACF plots of residuals have to be statistically insignificant, and it is evident from Figs 5 and also Fig 6 and Fig 7. This is the PACF, and the prior diagram was the ACF. Right, you then proceed to make inferences once you realize the model is good. So the inferences, you are going to have your forecast, then the output gives you the lower limit and the upper limit in the actual. If your forecast lies within the confidence interval, then that forecast will be a good forecast. But ourselves, we proceed on to plot the observed against the fitted for the package which we use enables us to do back focus from time 1 to the time when that is December 2022, and it also gives focus for the next year. So the focus are in red and the observed are in blue. As you see, they compare quite well, that the fitted model appears good enough. This approach, which is next of regressing, is not common in most time series texts, but we realized if the fitted is regressed against observed, if the model is a perfect one, you expect a complete straight line with no variations. But this one seems it represents well, but you cannot conclude from this plot. You need to fit the model and see the R-squared value. For the R-squared value gives the amount of variation in the dependent variable that is explained by fitting the model. So from this, the R-squared value, when we regressed the fitted against observed, was almost 91%, meaning the model explains about 91% of the variation in cells. Right? Anyway, I hope I wasn't too fast. I wasn't too slow. some non-mathematicians have gained something. I would like to thank you very much.